Thank you. So next talk is take your own share of the pie. And this is Sylvester is a senior researcher at Ericsson Research Budapest. He received an MSc in electrical engineering from Budapest University of Technology and economics. His main area of interest is traffic management, including control of resource sharing, network cooperation, scheduling, and dimensioning. So thank you, Sylvester.
Okay, can you hear me well?
Yeah, yes.
Okay, so it's a joint work with Eötvös Loránd University of Budapest, and I am the presenter they couldn't make. So what is our goal with PVPIE? We would like to create an AQM algorithm which is simple to implement, only drops or marks upon arrival to queues. And we would like to implement simple and scalable resource sharing policies building on the per packet value concept we published before, but I will give an introduction to that. And we would also like to keep target queuing delay building on the PIE AQM. So it's in effect a combination of the per packet value framework and the PIE AQM. So what is the per packet value framework? It's a resource sharing framework which allows a wide variety of detailed and flexible policies. It enforces these policies under all possible offer traffic combinations and scales well with the number of the flows. So it defines resource sharing policies for all situations by throughput packet value functions. It's done, for example, in a policy node. And then it proposes a packet marker at the edge of the network, which marks a packet value on each packet based on these throughput value functions belonging to that flow. So that's at the edge. And within the network, resource needs only need to maximize the total transmitted value. They don't. This results in implementing the policies without need for any flow awareness. So you don't need to know about these packets, to which flow they belong, or which is the policy of that packet. So it's marked on every packet, expresses the gain of the operator when the packet is delivered, and its relative importance on the packet in value per bits. And again, every resource node aims to maximize the transmitted packet value. So how to do that will be detailed in later. And then there is a congestion threshold value in this value space. Below that value, in an ideal system, below that value, all packets should be dropped. Above that value, all packets should be transmitted. And this value results from the combination of available capacity, amount of offered traffic, and the packet value composition of that offered traffic. And it's actually a pretty good descriptor of what happens in our system. And this complements end-to-end congestion control. We will show that it enforces fairness. Only low controlled loss has to be provided by the end-to-end congestion control, and only to avoid that packet problem. So if you have a single bottleneck, or if you have a network where that packet problem cannot happen, you can even live without congestion control. Of course, it's a question what happens to your application then. And with this, even incompatible congestion controls can coexist in a network. So what are these throughput packet value functions? This is actually a derivative of the utility function, and it defines the desired throughput of a flow of a class for all congestion threshold values. So what is an example for that? We have three classes here: gold, silver, and background. So, and the horizontal lines are congestion threshold values. So in the most congested case, which is the highest congestion threshold value, we say that a silver flow should get 4 times the throughput of a background flow, and the gold flow should get 2 times the throughput of a silver flow. But we can set throughput limits. So for example, we say if a background flow reaches 100 kilobits per second, then this weighting should change. And for example, if a silver flow reaches 1 megabit per second, then this weighting should change again. So in this other congestion threshold value, when the system is less congested, we say that a background flow should get 100K, a silver flow should get 1 megabit per second, and the gold should get the rest. And after that, after gold gets already 4 meg, we change the weights between background silver and gold from 4 to 2 to 10 to 4. And again, this is the throughput value function. This is only known at the packet marker. And from downwards the packet marker, these policies are communicated by packet marking only, and the resource node don't have to know anything about these policies, about the number of flows, only have to read these packet values. So how does a packet marker look like? The requirement is that if all packets below a congestion threshold value are dropped, then the throughput of the remaining packets shall be as defined by the TVF at this threshold. And it's fairly simple to imagine a simple packet marker, just quantize the function, make token buckets with the packet values and the length of the throughput region, and choose the token bucket with the highest PV where there are enough tokens. A simple example for packet marking. This is a very simple TVF already quantized with 4 levels. And we have 2 sources. One is 2 megabits/second, other is 6 megabits/second. So you can see that green is about 200K. Green plus blue is about 1 meg. Plus yellow is about 4 meg. And plus red is about 14 meg. So the 2 meg flow will only have yellow, blue, and green packets. So this is time here. While the other flow will have yellow and red also. But if you filter filter out the yellow and the red packets, then the speed of both flows remain 1 megabit/second. This is again completely unresponsive flows, and it's quite trivial. So because the marking rate of the blue plus green is 1 megabit/second. Of course, if you have TCP and you filter out these packets, TCP will adapt, and there will be only a few incoming yellow packets, which will be immediately dropped in this congestion situation. Okay, so as I said, the task of the resource nodes within a network is to maximize the total transmitted value. So the simplest algorithm is to always serve the packets with the highest packet value first, which is not practical because you want to keep ordering within flows at least. So the second simplest in concept algorithm is a FIFO implementation, and then when the queue becomes full, drop the packet with the smallest packet value first. But still, mid-queue dropping might not always be possible. So you have to have sort free, you have to be able to find and drop these packets. So we wanted to have a simpler argument, and that's when we thought of PIE. So what is PIE doing? PIE is basically having a controller, having a current queuing delay and the target queuing delay, and using a controller to control a drop probability for the incoming packets. For each incoming packet, a random number is generated, and if it is smaller than the drop probability, then that packet is dropped. And thereby it maintains the target delay and the given queue length. It's quite well published in the literature. There are improvements to it as well. So how we can translate PIE to the per packet value concept? What we do is that for each incoming packet, we maintain an empirical cumulative distribution function. So we basically make, for example, a histogram out of the incoming packets. We run the PIE machinery. We calculate the dropping probability basically the same way as PIE does. But instead of applying it directly and independently of the packet value, we take that value in the ECDF and update the congestion threshold filter accordingly. So if the packet value is larger than or equal to that filter, then we put that packet to the buffer, otherwise we drop it. And this is in our implementation, it's a very simple and first step in implementing this ECDF. We only implement it for the PIE control interval. It's 32 milliseconds in our simulations. And then we drop it. And we have seen some kind of like oscillations in this CTVs. So I will show that. And we actually sometimes had to increase the timing window for collecting this ECDF because there weren't enough data. So this part, when we translate the probabilities to filter values, is definitely a point to improve and to get further ideas on. So we implemented this algorithm in a simulator. We used Network Simulator Cradle to run a Linux cubic TCP implementation. We chose update periods to basically PIE per default 32 milliseconds. We had bottleneck rates ranging from 10 to 100 megabits per second. Target delays 40 and 20 milliseconds. I think we used 20 only because we wanted to compare to the PIE paper, which we used as a reference. And we had propagation delay, again, 40 and 100 milliseconds, the second values, again, to be able to compare to the PIE paper. And we have TCP users. They generated 1 or 5 TCP connections per flow, so a flow where we apply a throughput value function, so a flow has policies. So if in case the user had 5 TCP flows, these were handled together, even the packet marker didn't differentiate with them. We used 5 TCP flows because sometimes a single TCP flow wasn't aggressive enough, or the drop of a single packet was too high and the resource sharing wasn't as we intended. And UDP traffic is completely non-congestion controlled and high speed. Usually it's something like 60% of the bottleneck capacity. So if we have, for example, 3 UDP flows, as in simulations we have, they could already completely overwhelm the TCP flows if we wouldn't have any kind of resource sharing control solution. So this is the simplest simulation case. We have only gold and silver TCP sources, 5 TCP connections per flow, and we changed the number of flows from 1 gold, 1 silver, to 2, 2, 4, 4, and 8, 8. And using flow calculus and knowing the throughput value functions, it's possible to calculate the desired resource sharing. So what is what we defined? So if you know we have this number of sources, this TVFs, and this capacity, then it's simple math to calculate these desired shares. And what you can see, if we have not too many users, there are some deviations from the desired shares, but as the number of sources increases, the actual share got by the users is very close to the desired. And this is mainly because for the one user case, so this is the packet value filter versus the time. So what you can see here is that in many cases when we had only one users, we didn't actually have to put any packet losses because there was a burst of packet loss. TCP, it took time for the TCP flows, especially the gold TCP flows, to again reach its desired share. And during that time, we didn't have any chance to do anything. And as the number of flows increases, we have more chances to drop the right packet, thereby TCPs adapt to the right throughput. So again, the throughput results. So this was the region when it took time for the gold TCP flows to actually reach again the desired share. I also plotted the queue length here for this to compare to the PIE results. So this was the desired queue length, and you can see that when we increased the number of sources, we increased at 30, 60, and 90 milliseconds. There was a spike in queuing delay, but otherwise it was like around the queuing delay pretty well. And at the end, I will compare it to the actual PIE implementation. It's very similar to PIE. PIE also has this overshot, larger or smaller. So if you want to be, for example, always below this queuing delay, then you need some kind of different algorithms. It was in the PIE target, I think it was mainly keeping this target, but going above it when it's necessary. Okay, next set of simulation results is with non-congestion controlled UDP traffic. So the green flows here are UDP flows which can completely overwhelm the system. We have 3 of them, and then at 30 milliseconds, we start having TCP flows, increase them from 1, 1 to 2, 2, and 4, 4. And what you can see is that, again, if we have not too many TCP flows, then we are somewhat away from the desired share, but pretty close to them. And as we increase the number of flows, the flows get about the desired trend, also UDP gets smaller throughput as expected. So elaborating on this, I mean, what happens, for example, if we use PIE in this case? If we use PIE in this case, all packets are dropped with equal probability. So what will likely happen is that if you have like 10% or even higher probability of dropping TCP flows get basically no throughput by why the UDP flows get all of the capacity. And here, just by looking at the packet values and getting the statistics, you can achieve a very similar system where the implementation complexity is very similar to that of PIE, but you can stop misbehaving flows from gapping too much. One more simulation results with dynamic bottlenecks. In this case, we had I think one TCP flows, one silver and one gold, and we changed the capacity of the system. We changed from 10 meg to 50 meg to 100 meg, back to 50, back to 10. We wanted to see what's the transient behavior of the system. And again, transients, especially ramping up transients, take some time, but the system can realize the desired resource sharing pretty well. And in the final results I'm presenting, we wanted to compare it to the actual PIE resource sharing. So this scenario is as close to the scenario in the PIE paper as possible. So we have a 10 megabit per second bottleneck, 5 TCP flows, 2 UDP flows, and the target delay and round trip time is like in the PIE paper. And we actually, in the paper, we have another simulation results where we didn't reach the desired resource sharing as well as here. So what we did there is we increased the ECDF window. Again, ECDF window is how long you collect statistics about your packets to translate your dropping probability to congestion threshold value. So we had to increase that to actually reach this nice desired resource sharing here. And we also have to increase the number of TCP connections per flow. But if you take the values in the PIE paper, it was the two classes get about the same capacity. Why we suspect there weren't throughput values in the PIE paper, but what we suspect, because of the equal dropping probability, TCP flows there were completely overhand. And it's even with the default, it's not completely overhand here. And if you tune some of the parameters, you can again approach the resource sharing quite well. So, and this is the queue length of the two algorithm. This one is from the PIE paper. This is from our paper. So we have a slightly larger overshot here. And after transient, it keeps the queue length very similarly. So in summary, we created a PVPIE algorithm which can govern resource sharing by combining the PIE and the per packet value concept. Drop probability is calculated by PIE and is translated to congestion threshold value filter in the PPV concept. And this results a much more practical resource node implementation in this concept, because the previous implementation had to drop mid-queue, which is often not possible. And using NS3 simulations, we have shown that it can realize the desired resource sharing and keep the target queuing delay. Of course, we have some further work to do. We need further simplification. Actually, keeping the ECDF can be still quite costly, especially for high-speed links. Of course, there are other options, but we have to look into these options. And also, the filter thresholds has to be stabilized by also improving transient behavior. It's pretty okay right now if you have a few number of high-speed flows. This filter can be switched on and off fairly often. Or if you have many UDP flows, there can be problems with it. Of course, PIE itself is tuned for TCP flows, so it's not surprised that it's not behaving like perfectly for UDP flows. On the other hand, it's actually somewhat surprising that it's working that well with UDP non-congestion controlled flows. Okay. And that concludes my presentations. Open for questions.
So questions?
Yeah, you actually mentioned my question already on the last slide. I was wondering how much computational complexity and state you actually need for the inverse CDF, and how you maintain whatever the last window of values, of measurement values you have. How do you implement this in practice? Do you have, or up to which speeds would you assume that you can maintain this? Just curious.
I don't have a strong assumption. I'm not quite the node implementation guy. In the simulator, of course, you can do whatever you want.
It doesn't matter, right?
Yeah.
And when it comes to practical implementations, we are thinking about actually practical implementations. I can't really go into many details. Of course, you can always maintain a histogram and erase the histogram from time to time. You can quantize the value space or use smaller value space. We use the single byte value space here for the per packet value. So it's not like amazing, not like a huge value space. But we are actually, if you want to implement this concept like at its brightest, then you might want to use 2 octets and having like 2 octets like 60
per flow, right? Per flow, right? Or was
no, the histogram is per again.
This was per class.
No, this is per bottleneck. So again, I mean, the thing with the concept is that at the resource node, you don't know about classes, you don't know about flows, you only know about packet values. So you need a single ECDF per resource node.
Then that is probably okay.
So it's probably fine. I mean the whole thing with the concept is that scale varies with the number of flows because you don't know about the number of flows at all at the bottleneck.
All right, thanks.
Hello. The question is in a similar context about flows, probably. So the idea, if let's say my packets belong to the economy class, not the gold one, right? And I'm most preferred to be dropped, my packets to be dropped from the flow because of this of the mechanism. Does PIE also take into account the age of the flow? For example, assume if my flow packets are constantly dropped, their value will start maybe increasing after some time. Else my session will be ditched or will be impaired. Is the age a factor in this, for example, or?
I mean, the thing is in the packet marking. So if your flow is responsive and your packets are completely and constantly dropped, then your flow rate will be likely below your fair share rate. And then the packet marking algorithm will make sure that all your packets has value higher than the congestion threshold value, which means that none of your packets will be dropped until you are above your fair share.
So it compensates for, okay.
Yeah, I mean, it's compensated by packet marking. So let's say your fair share is 100 megabits per second, congestion threshold value is 100. And then as if you are transmitting with 99.9, again, I'm talking about a completely ideal system, but then all your packets will have value higher than 100.
Okay, thank you.
Any other questions? I wanted to someplace we have this quote that, to every problem there is a solution that is obvious, simple, and always wrong. And when I was looking at your paper where it's like, well, we have this tool, we have this other tool, we should put them together. And I was really worried that you were going to trip over this is obviously the right thing to do. It's simple and it's going to be obviously wrong. I'm really glad that it turned out as well as it did. But thank you so much.
Thank you.